Right. Hello, guys. Welcome back to 15.8, triple integral in spherical coordinate. So as I mentioned last time, the now three section will be about coordinate transformation. So 15.7 deals with the cylindrical coordinate. 15.8 deals with the spherical coordinates. And spherical coordinate is kind of a coordinate that fits better with respect to symmetry of a point, whereas cylindrical coordinate treats better with symmetry with respect to a line. So let us first define what spherical coordinate is. It is slightly different from the previous coordinate, like polar coordinate, so we will have to be careful with the notions. So in R3, we may represent again a three tuple XYZ to be another three tuple rho. This is pronounced rho, theta, and phi. And how do we define this, guys? First of all, rho is a radius between the point and the origin. So it is simply x squared plus y squared plus z squared, right? And theta, called the azimuth angle, that is not really commonly used. You can just call it theta. So theta is the same as the cylindrical coordinate or the polar coordinate. It is the angle between the positive x-axis towards the planar point x, y, 0. So in some sense, it is the same theta as the polar coordinate of xy, or the same data as the cylindrical coordinate of xyz. Thirdly, phi is the angle between the positive z-axis together with the line formed by the origin connecting xyz. So if we connect the origin and xyz, then this angle is called phi. So first of all, it is rather simple to observe what is the domain for this, guys. Rho obviously is always positive because it is a distance between the point and the origin. Whereas theta goes from 0 all the way to 2 pi, right? And phi goes all the way from phi to pi, okay? So phi is always within 0 and pi. And in particular, phi is usually called the polar angle. And now here, the name of this data phi is not really important. The important thing is that you know how and what this notions represents, okay? So let me repeat this again. Rho is the distance between the point x, y, z and the origin, where theta is the same angle as in the polar coordinate or cylindrical coordinate. It is the angle between the positive x-axis together with the planar point x, y, 0. And phi is the angle between the z direction, the positive z-axis, together with the line created by connecting origin and xyz. So phi. Right. So obviously, the first thing we have to do is to know how to translate between spherical coordinates and Cartesian coordinate. So let me do that. First of all, it is rather simple, as in the cylindrical case, to translate from the spherical coordinates towards the Cartesian coordinate. So let us see. This blue line here is rho, right? So it is rather simple to find the height z, because given that this angle is phi, then this angle is also phi. So the height is simply given by definition, rho times cosine phi, that is z. And to find out x and y, we first find out the base here, and then we project the base onto the x-axis and the y-axis. So again, by this right triangle, we see that the distance from here to here is rho times sine phi. So this here is rho sine phi. Now, if we project it onto the x-axis, then by the definition for the angle theta and this right triangle, we have rho sine phi multiplied by cosine theta will give us the correct x coordinate. So x coordinate will then be rho sine phi cosine theta. And similarly, y will simply be rho sine phi and sine theta. So these are the coordinates in x, y, z represented by rho and theta and phi. So let me repeat this again. X is rho sine phi cosine theta. Y is rho sine phi sine theta, whereas z is rho cosine phi. Now, to translate x, y, z back to rho, theta, v, first of all, the radius is very simple. You simply calculate the distance from the origin towards the point x, y, z. So x squared plus y squared plus z squared taking square root. Secondly, theta, as usual, in the cylindrical coordinates and in the polar coordinate, we find an inverse tangent towards y and x, and we add a correction term depending on the quadrant. If xy is in the first quadrant, then we add nothing. If xy is in the second or third quadrant, then you add pi. And if xy is in the fourth quadrant, you add 2 pi. Again, this is just for the sake of to adjust the domain for inverse tangent, because inverse tangent lies within minus pi over 2 to pi over 2. To adjust that, we have to shift the domain a little bit. As for phi, it is also quite simple. We use the same logic. There's so many ways to find phi, because you can do things like maybe take an inverse cosine of z divided by rho. But just to make things consistent, I want to use inverse tangent. So let's see. To find the inverse tangent of phi, we see that x squared plus y squared basically is, oh, actually, let me take square root, is rho sine phi, right? I'm basically saying this line, rho sine phi. So by dividing this guy, rho sine phi, together with rho cosine phi, which is this divided by this, gives you tangent phi. That means tangent inverse of tangent phi will give you phi. And again, to adjust the different coordinates, we would like to translate the angle back by pi if the corresponding angle is less than 0. So that is when you have some inverse tangent angle being negative, then that means that you're within the domain of minus pi over 2 towards 0. And in which case, we want to add the angle by pi, right? Okay, now let us try some example. So first of all, let's find the spherical coordinates of root 3 minus 1, minus 2 over 2 root 3. And yeah, basically the radius is again taking x squared plus y squared plus z squared. And after some calculation, you get 3 plus 1 plus 12, and that'll be 16. So you get 4. Then for the so-called azimuth angle, you want to find out a tangent inverse of y divided by x. And this guy is obviously in the fourth quadrant, right? So we add a correction term by 2 pi. And this guy, which angle has tangent to be minus 1 over root 3, that is minus pi over 6, right? Minus 30 degrees. So you get 11 pi over 6 in the fourth quadrant. Then for the polar angle, phi, again, it is simply tangent inverse of x squared plus y squared taking square root divided by z. So this two guys and this guy. And obviously this is a negative value. So we add pi to correct the angle. And this guy is minus 1 over 3 again. So it is minus pi over 6. Adding with pi gives us 5 pi over 6. And therefore, the spherical coordinates is given by rho theta phi, where rho is 4, theta is 11 pi over 6, and phi is 5 pi over 6. I want to emphasize here that sometimes in the physics literature, theta and phi are used differently, which means that usually they use phi to be the azimuth angle and theta to be the polar angle. It depends on the context, but in our calculus course, we will always assume theta to be the polar angle, the same thing. In the polar coordinate, sorry, let me make this precise. It is not called a polar coordinate in this three-dimensional system, but it is same as the angle in the polar coordinate in two-dimensional space, and the same as the angle in cylindrical coordinates in three-dimensional space. So we always use the same notation theta. And phi is always the axis, the angle between the z-axis towards the line connecting from 0 and the point x, y, z. Okay, and now to translate the Cartesian coordinate from spherical coordinate is rather simple. So let us recall the formula. For x, it is rho sine phi sine cosine theta. And y will be rho sine phi sine theta. whereas z will simply be 4 cosine phi. So plugging in the corresponding angle, pi over 2 and pi over 4, you can get something in this coordinate, 0, 2 root 2, and 2 root 2. So I would say that you don't really have to memorize this because somehow if you have this picture in mind, then that just comes in naturally. You have rho cosine phi, rho sine phi, so rho sine phi cosine theta, and rho sine phi sine theta. Okay? Right. So now we're familiar with the spherical coordinate. We can now perform the integration over this coordinate, just like in the case in the cylindrical coordinates. But the thing difference here is that we have to reevaluate the volume change under this spherical coordinate. Back in the topic on polar coordinate, I believe it is 15.3, we actually have calculated the small area using polar coordinate, right? We didn't do that in the previous video, 15.7, because basically it is the same using the cylindrical coordinate as using the polar coordinate. But now we're in an inheritable region, so we have to do that again. So let us compute the small section of area, of volume of the solid. So this is a very nice graph. So I basically copied it from textbook. You can see that connecting every point towards the origin gives you an angle of the difference between phi, because this is the angle difference between this phi1 and this phi2, right? So that is delta phi. And obviously, the so-called maybe thickness is delta rho. That is the difference of distances from the outer layer towards the origin and the inner layer towards the origin. Lastly, there is a another thickness in this direction of delta theta. So those are basically the three different components in this small solid thing. And now, how do we compute this volume in terms of rho, theta, and phi? So basically, it is. Let me see what I'm writing here. Oh yeah, okay. So we want to calculate this solid, which looks like mostly like a let's say it's a sector kind of thingy object. It is a small piece of disk, right? So first of all, what is the distance here? That is rho I sine phi k, right? Let me emphasize here. I pick a particular point, which is in the Riemann sum in the um, finite grid. We cut the domain to finitely many rho I theta j and pk, right? And want to evaluate a small fine region to make sure that you have the same kind of representation of Riemann sum as the condition coordinate. So in this case, we choose rho I, theta j, and phi k. Where in particular, you can get that this distance is rho I sine phi k, because by definition, let me see. Okay. Because by definition, you simply project this rho I, down here and down here, where this guy is rho I sine phi k, and the height here is rho I cosine phi k. Okay. And now, what we want to do is to find out this particular length, because this whole thing simply looks like a rectangular object, right? So it's base times height. It's width times three-dimensional object. So base times width times thickness, maybe, if that's the term. So we want to figure out this three object. And why do we figure out this first? Because if we have the radius, then we can evaluate this, let's say, the width. So if this is rho I sine phi k, then by the formula of the circumference of circle or a sector, you simply have Ri multiplied by delta theta to get this small length, right? Which is Ri delta theta given by rho I sine phi k delta theta. So that is one of the length of this rectangular object. And secondly, to evaluate the height, height. Let's say this is height. you'll simply have rho times delta vk, again, by the formula for the sector, right? So you have this guy. And the thickness here is delta rho. So you simply have this guy multiplied by this guy multiplied by this guy, which is this formula here. So combining everything, you have rho I squared sine pk and the infinitesimal term, delta rho I delta j delta pk. And these are the small tiny terms in the xyz domain. So basically, for every small solid given by this rho I delta j and pk, we can compute its volume by rho I squared sine pk together with this infinitesimal term. In conclusion, on this particular region where we have a fixed common boundary for data and phi within alpha and beta, gamma and delta, and rho is usually given by some functional boundary in terms of data and phi. Then this is in terms of partition value. If we want to evaluate this using the spherical coordinates, then you have, let's start from alpha. And then phi. And finally, the coordinate of rho. You have the same function. Don't forget to replace your coordinates. Okay, this will take some time. Sine phi, sine theta. And finally, z is cosine phi. Okay. And we have the additional term, which tells us that the dV, the infinitesimal volume here, is given by this formula, right? So let us replace that. You have, let me use red. Rho squared sine squared, rho squared sine phi, and that's all, right? Don't forget that term. And then it's the usual thing, d rho. Oh, this is a big formula. d rho, d phi, and then d theta. Okay, that's a real. So that's the formula if you want to translate your triple integral from a Cartesian coordinate towards the spherical coordinate. The additional term is now rho squared sine phi. So previously in the polar coordinate and center coordinate, it is r, right? It's always r. The r is the radius, which is the distance between xy and the origin, not xyz. For now, it is the distance between xyz towards the origin squared, and then you have an additional sine phi here. So then let's try some example. This is the utterly most important formula for this lecture. Okay. So again, let us find a volume of a ball of radius r. We have done this 1,000 times. We can do this by the washer method, which is rotating the surface y equals to square root of r squared minus x squared using the respect to the axis. Or we can use the cylindrical coordinates. In this case, let me use the spherical coordinate. So by describing the solid, it is basically xyz, which satisfy the constraint x squared plus y squared plus z squared less or equal to r squared. And obviously, in the spherical coordinate, it is very simple. It basically goes around the theta, right? Theta goes from 0 to pi, where phi goes all the way from the positive z-axis towards the negative z-axis. So it's 0 and pi, where rho simply goes from 0 to r. So we can see that in the spherical coordinates, everything becomes a constant. And that is very kind of intuitive because that is how spherical coordinate is created. It is designed to evaluate the integration respect to some point symmetric domain. Okay. So as mentioned, the volume is simply integrating 1 over the whole thing. And so 1 times the rho squared sine phi gives us just rho squared sine phi. Where rho goes from 0 to r, phi goes from 0 to pi, and theta goes from 0 to pi. So first of all, theta goes from 0 to pi gives you the integration to pi. And sine phi, integrating over phi is minus cosine phi. Plugging in pi and 0 gives you 2. Whereas rho squared integrating gives you rho cubed divided by 3. So this gives us r to the 3, r cubed divided by 3. And so combine that everything, you should get 4 over 3 pi r cubed as usual. So you can see that this is much simpler in comparison to using maybe Washer method or cylindrical method, because this particular coordinate is designed for this type of region. Right, let's deal with the next example. So this is from our textbook. We want to find a volume that lies within the sphere. So whenever you see a sphere, it is usually better to use spherical coordinates, usually. And I want to find it above the xy plane and below the cone. Oh, actually, okay. I evaluated the wrong thing here. Let me just change the problem to make life easy. To let me say lies within. Yeah, I can see that I also make mistakes. Let's say lies within the sphere and the cone. That is what I computed. Right. I also encourage you to do the original problem. So let me first mention what I did wrong here. Basically, for this sphere, you have this spherical object, right? And for a cone, it looks like this. So what this problem originally asked us to do is to find the region between this cone and this sphere above the xy plane. But what I actually compute is this cone thingy. So yeah, that's a little bit different. But anyway, you can simply subtract my answer by the volume of the half ball, and you can get the corresponding answer. But yeah, first of all, let us do this problem, which will evaluate the volume between this cone and this sphere. Okay. So let us rewrite this spheres, this surfaces in terms of spherical coordinates. First of all, what is x squared plus y squared plus z squared to be 4? It is simply the distance being 2, right? So we can see that basically in spherical coordinates, the sphere becomes a really nice level surface of rho. And for the cone, z equals to square root of x squared plus y squared. You can see that left-hand side is rho cosine b, and the right-hand side is rho sine b. Don't forget that sine b is always positive because b is within 0 and pi. And so this tells us that tangent phi is basically 1, or that phi is fixed to be power 4, which is kind of intuitive because you see that this cone basically describes every point with the polar angle of 45 degrees, right? So you can see that again, this region is a very, very simply described region in spherical coordinates where the distance rho goes from 0 to 0 to 2, and the distance goes, the angle goes around from 0 to 2 pi, and phi goes from 0, don't forget 0 is the positive z-axis, towards pi over 4. Okay, it is again a constant boundary region. And yeah, this is a good chance since I evaluated this problem wrong. So try to do that the correct way and describe it similarly using rho, theta, and phi. So let us carry on solving this problem, the region between these two guys. So we have that the volume is given by, again, the triple integral over 1. And so you have rho squared sine phi as your integrand, and constant boundary for each of these guys, for phi, theta, and rho. And it turns out to be something like this, okay? So as I mentioned, if you want to evaluate the correct answer for this original problem, problem 30, then it's basically this guy. This is the whole ball volume, right? Divided by half minus our answer here will give you the correct answer. But also, as I mentioned, I encourage you to try to evaluate that directly by describing it using rho, theta, and phi. Okay, that is method one, but we can also use cylindrical coordinates. So there is no particular coordinate that is restricted, but we just to see which coordinate is better to use. And basically, in some sense, cylindrical coordinates and the spherical coordinates are kind of interchangeable because they all deal with the symmetry somehow. In this case, the sphere is symmetrical with respect to the origin, right? Whereas the cone is symmetrical with respect to the z-axis. So somehow both kind of surface motivates us to these both different coordinates. So in this case, if we're evaluating using spherical coordinates, then again, the angle basically goes from the azimuth angle basically goes from 0 to 2 pi. With r, don't forget, r is not the distance between x, y, z and origin, but x, y, and the origin. So it goes from not 0 to 2, but 0 to the 2. Okay? Here, 0 to the 2. It is basically 2 times the uh cosine of phi. So that is pi over 4, because pi over 4 is 1 over 2. And for the cylindrical coordinate, we have to figure out the height, right? The z. So z basically goes from the cone towards the sphere. And that is basically going from x squared plus y squared, taking square root, towards root 4 minus x squared plus y squared. So evaluating using the cylindrical coordinates, we have each boundary here. And also don't forget that you have an extra r in the cylindrical coordinates. And then it's simple calculus. So you do integration over z, and you evaluate on the boundary, and you finally get the same answer. Okay. So just to mention here, a small arrangement on how this coordinate plane looks like. So the following table is the coordinate planes for each coordinate. We know that in Cartesian coordinate, which we learned in section 12.1, that basically the different coordinate system, x equals to a, y equals to b, z equals to c, is just a plane that is horizontal to the yz plane, parallel to the yz plane, parallel to the xz plane, and parallel to the xy plane. That's the usual coordinate plane, okay? Or level surface of x and y and z. And for cylindrical coordinates, we know that when r equals to a, it's basically describing every points where the xy coordinate have the same radius. So it looks like a cylinder. Okay, this is when r equals to a particular distance a. A is here. And theta is b means that xy share the same polar angle, right? So it is basically a plane which cuts the angle b towards the x-axis, a slanted plane. And z is the same thing. So this is exactly the same thing. And don't forget you have this extra r when you evaluate the integration. We will introduce this notation afterwards in section 15.9. This is called Jacobian. But basically, you have to add this r whenever you're doing the cylindrical coordinate integration. As for the spherical coordinate, which we introduced this lecture, we know that rho equals to a is basically a sphere, right? It is any point with distance a within the origin, which I should include here. Let me draw it. So for any point, you have a distance. For any point, you have a distance of a within the sphere and the origin. And similarly, the theta is the exact same thing as the cylindrical coordinates. So the coordinate plane theta equals to b is basically, again, a slanted plane, which cuts an angle of b within the positive x-axis. As we mentioned, the coordinate plane for the polar angle phi given by c is basically a cone, which every point shares the same polar angle phi. Okay, so that those are the different coordinate planes with respect to the different coordinates. And you can see that it basically tells us when do we want to use this different coordinate system. If you're describing a cylinder, then obviously you want to use the cylindrical coordinate because this becomes a constant bound. And if you are dealing with either a cone or a spherical region, then you want to use spherical coordinate because that makes the boundary to be constant instead of functional boundary. All right. So after that, I believe, yeah, this is the last example. So this is also from our textbook. We want to evaluate this x squared plus y squared plus z squared to the 3 over 2 over this coordinate system. So first of all, obviously, we have to figure out what this thing looks like. Obviously, there is some symmetry, right, between x and y and z. So we might want to use the maybe cylindrical coordinates or the spherical coordinate. But before doing so, we have to find out what this region actually makes. So basically, you see that in the first two boundary for -2 for x and y, basically -2 and 2 over x and plus minus square root of 4 minus x squared over y. This basically tells us that you are dealing with the region of x squared plus y squared that's equal to 4, right? A disk of radius 2, right? So that is why I written down here. You should be familiar with this kind of notation here. When you see this kind of shit, immediately know that, okay, we're dealing with a disk. And what is this guy? So we're dealing with a z upper bounded by 2 plus this square root guy and 2 minus this square root guy. If you arrange the inequality by subtracting both sides by 2, you get this. That's equal to z minus 2. That's equal to this guy, which is this inequality, right? By squaring both sides, you should get x squared plus y squared plus z minus 2 squared less or equal to 4. So that is basically a ball, maybe a sphere of radius 2 with the center at 0, 0, 2. So you can see that we're basically integrating over this ball where this is somewhat natural because the whole region will be the xy disk of radius 2, right? And then z obviously is bounded below by the lower hemisphere, which is this guy, and bounded above by the upper hemisphere. So now, how do we describe this region using spherical coordinates? Obviously, theta goes from 0 to pi, that is very simple. And phi actually goes from 0, which is the positive x-axis, towards the xy plane, which is 90 degrees. Okay? So you don't have to treat anything below the xy plane. So that's from 0 to pi over 2. And for the rho, the radius, it is a little bit more tricky. So you can do this in two ways. First of all, by simple geometry, we see that for a particular fixed theta and fixed phi, let us find out the distance rho. So obviously rho goes from 0 towards this point, right? But what is this point? How long is this point towards the origin? By definition, every radius of this ball is of length 2, so 2 and 2. And this is phi, right? So by definition of the trig function, this guy here is 2 cosine phi. And so this whole thing here is 4 cosine phi. So for a fixed coordinate, theta and phi, the rho goes from 0 towards 4 cosine phi. You can always do that by, again, plugging everything back to this equation. Because you see that if we plug in x squared and y squared by rho sine phi cosine theta and sine theta, you get rho squared sine phi squared, whereas this guy gives you rho cosine minus 2 squared. Arranging an equation, you can get that rho is basically that's equal to 4 cosine phi, which is consistent with our previous notation here. So anyway, this will be our corresponding coordinates boundary for the integration. So this 3D integration will be 0 to pi over theta, 0 to pi over 2 over phi, and 0 to 4 cosine phi over d rho. And this guy is basically rho cubed, right? Because we have square root of x squared plus y squared plus z squared is rho, and you're taking the cube of that, so rho cubed. And you have the extra term here, which will be a d, rho squared sine phi. And then it's simply a very naive version of integration. Doing respect to rho is a rho phi, right? So you get 1 over 6, plugging in the corresponding boundary for cosine phi to the power of 6. And you don't have to panic because basically you have this sine phi here, which serves as a differential for cosine phi. Sine phi d phi is minus d cosine phi, right? So you're simply integrating cosine phi, which you get 2 pi 4 to the power of 6 over 6. And then finally, minus 1 over 7 cosine to the power of 7. Plugging the corresponding angle for phi, which is 0 n power 2, you get this number, 4096 over 21 pi. Okay, so there's nothing much in this section, basically just as in the cylindrical coordinate section, the important formula is this formula. We need to know how to translate from the Cartesian integral into the spherical integral. And the only difference is you have to plug in the corresponding Jacobian thingy, rho squared sine phi. So yeah, you have to know how to translate between spherical coordinates and the Cartesian coordinates. And to evaluate an integration, you use this formula. And to be precise, how do you determine a region in terms of rho, theta, and phi? You basically write down the surfaces. So just like, let me see, maybe first for this. In this example, I write down the sphere and the cone in terms of rho, theta, and phi, which coincidentally is some constant plane. Rho equals to 2 and phi equals to pi over 4. And in this case, you can see that we're not dealing with a coordinate plane, but something in terms of a functional boundary. And it is the same, you figure out the boundary, writing them in terms of the rho, theta, and phi, and you should get something like this. Rho equals to 4 cosine phi. That is the surface of the sphere with radius 2 and center 0, 0, 2. Okay, so that concludes our course on the spherical coordinates. The next lecture will be our last lecture before midterm, and also before we introduce chapter 16. So that'll be the last section of chapter 15. We'll be ending our integration course and start dealing with some theoretical results. So let me sort of foreshadow what we're doing next. So 15.9 will tell us how do we translate coordinate in a general formula. We have already introduced 3 different types of coordinate transformation. One is the polar coordinate in 2D, and we also introduced the cylindrical and spherical coordinate in 3D. But this can all be boiled down to one simple formula, which is called the Trainer variable formula, which we will introduce in 15.9. And that will sort of help you to arrange what you have learned for now and to make everything compatible in some sense. Later on, we will be doing chapter 16, which is a chapter on integration theorem, telling us how the fundamental theorem of calculus plays a role in 2D and 3D space. So I will see you in the next video. Have a good week.